All right, so today's lecture we will continue from where we stopped on Monday, and we'll try to finish the content for the chapter 1. And last lecture we stopped at the concepts between for the systems and the control volume. Basically, what we are seeing is that for system for a system it will be closed, which means that is defined by the specific mass, right? The total mass in the system will always keep constant, no matter what the boundary of the system maybe can keep changing. Control volume, on the other hand, is not defined by mass. Is defined by the volume. It's defined by the space coordinates. It's basically, the mass inside a control volume will not be constant if there is a flow flux. Mass flux can flow in or flow out from this control volume. And so some comparison between the, summarization, the difference between the system and the control volume, right? In the system, the mass is definite, right? And its boundary do not need to be definite. For example, that if you specify some mass here at this t0 moment, and with time is going on, this flow element, they can keep moving because it will have its own velocity, right? So you can see that there are boundary, right? There are physical location, their space location will be keep changing, right, with the time. So this but the mass inside the yellow region with different time, they will keep constant. So this is a system approach. Basically, is that in this approach we just study a piece of fluid elements which has some which constant and which mass is will be constant. Control volume, in the other hand, is that you just defined by the location, right? So its boundary is usually definite. Okay, and so basically, in a control volume approach, okay, after we define this control volume, we will fix our observation point at this point in this control volume, and the flow can this flow can flow into or flow out. Flow into or flow out from this control volume.
So is what you're saying, in a system, the boundaries are infinite, and for a control volume, the mass is infinite?
Yes.
Okay.
Yeah. And you see that it's kind of for the control volume, right? You see this blue line, so if they are the flow streamline, this means that the flow can flow in, and they then stay inside this control volume for a while, and then after some time it will flow out from this control volume. Okay, so this is two different way that to study the fluids. And in fluid mechanics, okay, we usually using the control volume way, because that for the system approach, that means that we need to track this physical fluid element along its streamline, right? This is the blue line, is the streamline of the flow. So we need to track this fluid element or you can also call this fluid particles in this region. We need to track this particle along this streamline. That means that if you do experiments, you want to measure the properties of this yellow region, this system properties. You have to move your your experiment equipments together with these fluid particles, right? So that if the particle is here, you want to measure its velocity, you have to put your equipment at this point, and when this particle is keep moving, you need to keep changing your the location your measurements. It's not easy to do, and most times it's impossible to do that. Okay, for example, that if you have a airflow around an airplane, right? You see that you know, the flow before the flow hits the wings, and for the flows in above and down above and below the wings, and when the flow, you know, go to the tails of the wings, the flow direction change a lot. Okay, and impossible you do that kind of measurement so that you can know that the whole flow field will be no. Okay, but usually what we did is that you know, with using the control volume approach, where that since the physical location is fixed, right? So we just put our, you know, experiment equipment in that position. We do not change it, right? We will just report that you know, all what the velocity, what the density, what the temperature inside this control volume with different time. Okay, so that's why that you know, the control volume approach is usually more, you know, usually is a more friendly way we will going to use in the fluid mechanics problem.
So is what you're trying to say in the control volume, mass is flowing through the control volume?
Yeah.
And then what's flowing in the system?
In a system, there is no mass flow in or flow out. Okay. So the mass in this region, in this yellow region, you know, although you see the size is different, right? It keep changing, their boundary is changing, but the total mass inside is not, it will keep the same. You can think about that. For example, like in the beginning, there are like 100 fluid particles here, and at time t1, there will be still that 100 particles, but maybe their distance between each other will become larger. And on the T2, you know, the same 100 particles. On T3, you know, also the same particles. But because these particles, they have their own relative velocity. So if you want to draw a boundary to include all the particles, this boundary is keep, you know, deforming.
So it's the particle that's flowing.
Yeah,
it's the particles that are flowing in the system,
yeah.
right?
Yes.
Okay.
Yeah. So I can give you more explanation on this. Let's first thinking about the conservation mass. Okay. On the top, okay, is a system. You see that the dashed line, the right dashed line is the boundary of this system. And because it's closed, the total mass inside this system is constant, right? And if we want to using the concept of conservation mass, so what it will be? So basically, in the system is very simple. It just means that you know, this big M means the total mass. Okay, the mass of this system will be constant. So this is a mathematical equation, the governing equation, the mass conservation equation for the this closed system. You can also, you know, write this equation in another way. Basically, you can see that the change of this is total mass in this system regarding the time will be 0, which means that you know, along with the time, right, there's no change for the total mass inside this system. So these two equations is the governing equation for the mass conservation equations for the for closed system. Okay, it's very it's relatively simple. Okay, but if we look in the control volume, okay, the bottom one is the control volume, and this dashed line is defined what the region this control volume will be. Okay, and you can see that you will have the inflow, okay, incoming flow, like where the flow, my scene is the flow into this control volume. You will also have the outlet flow where the flow will be flowing out. Okay, so in this case, if you want to do the mass conservation, okay, so what this mass conservation will give you? So this will be the equation of the mass conservation will give you. It's basically telling you that you know, the mass flow, you know, flow into the CV. This CV means the control volume. Okay, the mass flow into the control volume, and minus the mass flow flowing out from the control volume. Okay, will be equal to the amount of mass flow increased inside the control volume. It's very easy to understand, right? Because when your mass flow flowing in, you add the mass to the control volume, and when you have the flow flowing out, that means that you reduce the mass inside the control volume. Okay, so flow in minus flow out will be the, you know, overall increasing of the mass of the control volume. Okay, and if I write this, you know, this observation, okay, in a mathematical way. So it will be m dot in. This m dot, okay. This m dot. Do I have some? Can I write something? No? Oh, I cannot write. Hold on a second. Okay, let me give me 1 second. Let me put this in the whiteboard so I can write something. Okay, so it will be here. Okay, so this m dot here. Okay, this dot means the mass flow rate. Okay, is defined as dm of dp. Okay, so the unit will be kilogram per second. Okay, so it's different with the m itself. M itself is just the mass. Okay, it's kg. It's the mass. Okay, the unit is kg. So do not confusing with these two. So basically, if I write this in the equation form, it's basically telling me that m dot in minus m dot out, okay, flow in minus flow out will be changing of the mass inside the whole control volume, you know, regarding to the time. Okay, so from this comparison, you can see that okay, if we're using different way to study, okay, if we're using the system or we're using the control volume, your result equation will be different. Okay, this is what the equation will be, and this is the this equation is what the equation for the system, and this is the equation mass conservation equation for the control volume. Okay. And similar things. Okay, let me give you one more example. So let's consider the conservation of energy. Okay, not only the conservation of mass, but also conservation of the energy. And we have a closed system, right? So this is if you're looking for a closed system, the conservation of energy is just equal to the change of the total energy inside this system will be equal to the total heat absorbed from the surrounding minus the total of work done by the system to the environment, to the surrounding. So this is if you took the thermodynamics class before, so this is just the first law of thermodynamics. Okay. Well, thermodynamics. Because that in thermodynamics class, we usually just using the system to study. Okay, in thermodynamics we do not using the control volume. In the thermodynamics we usually just using a closed system to study. And so this Q larger than 0 means that you know, system means that heat transfer into the system. Okay. So that's why it means that you have the plus sign here, means that because that Q larger than 0 means that the energy is from Q larger than 0 means that the energy is from the outside to. I don't know this arrow. Okay, remove this arrow. So Q larger than 0 means that the heat is from the outside going into the system, and work larger than 0 means that system done to the environment, to the surroundings. Okay, surroundings. So that's why let me remove this arrow. So that means that this W is larger than 0. That means that this system do the work to outside. So that's why it means you have a minus sign before the delta, before the W. Okay. So this is the conservation of the energy for a closed system. Okay. And but if you look in the control volume, there will be two additional term here. Why? Because that in a control volume, you will have this flowing in, right? And the flow, this mass flow into this control volume. It will also bring the energy into it, like this additional, this additional flow flowing in with their own total energy. And for the flow flowing out, okay, you will also have this control will also lost the energy, because that the flow flowing out will also contains their own total energy, part of it in total energy. So for the control volume, we will have two additional terms here for the for the energy. It's like the total change, the total increasing of the energy inside the control volume will be total heat absorbed minus the total work done to the surrounding, plus the total energy flow into the system minus the total energy flowing out of the system. Okay, so if you look in these two equations, you will see that if we study using the different system, okay, if it's a closed system or if it's an open control volume, you will see that the equation for conservation of energy will also be different. Do you guys have any question here? Because this is the important part.
Yeah, real quick question. Can you repeat what having W greater than 0 means?
Okay. So because that I just want to using the same definition with your thermodynamic class. Okay. In your thermodynamics class, this W larger than 0 means that let me rewrite it maybe more clearly. So W larger than 0 means that work done by system to surroundings. Okay, so that means that this work is done done by this system to outside, okay, to the environment. Okay, so that means that if this work is larger than 0, means that this system will lose energy because they done the work to outside, so that they have to using their own energy to to convert this to the work, right? And Q is in another difference. Q larger than 0 means that heat transfer into the system, which means that the outside transfer the heat into the system. That's why is that I remove this arrow here. I remove this arrow here. So if you're looking this way, like a heat is adding the Q larger than 0 means that you're adding the energy. W larger than 0 means that you're losing the energy. Okay, so that's why you have plus sign for the Q and minus sign for the W. Do I answer your question?
Yes, thank you very much.
Okay, let me also remove this one so that you won't be confusing. So Q, remove this one.
Professor, just a quick question.
Sure.
When Q is less than 0 and W is less than 0, is it just the opposite of the statements you've already written?
Yeah.
Okay.
If W is smaller than 0, that means that this work is done from surrounding to the system, not system to surrounding. So the system will gain the energy. And same thing, if the Q is smaller than 0, that means that this heat is transferred from system to outside. So the system will losing the energy. Okay. So just if Q is smaller than 0, just reverse this direction. If W is smaller than 0, it also reverse this direction.
Okay. Thank you, Professor.
No problem. Okay, so here you can see that the difference that if we're using different systems, if we're using different concepts, right? So your equations you have the different forms actually. And so this is a example problem on the textbook. So we will go through it. Take some time to read the problem description. Okay, it's saying that you have water flow through this pipe. Okay, and this pipe, their cross-sectional area will keep decreasing. Okay, on the flow direction, and we know that the size of the diameter inlet and the diameter of the inlet and diameter of the outlet. Okay, exit. And if we also know flow velocity at the inlet, right? So we want to compute what the flow velocity at the exit. So in these cases, okay, because we have the flow in and flow out, right? So we using a control volume concept. We draw this blue line on this picture, okay, as a control volume, and so you have the mass flow in, you have the mass inside the control volume, and you have the mass flow out. And one important concept you have here is called they call this is steady state flow. Okay, this word is very important, steady. So what steady means? Steady means that basically means that there's no change on time. So remember that what we write the mass flow rate before. We have this m dot in minus m dot out equal to dmc change of the mass in the control volume regarding the time. So let me rewrite this equation here. So we have this m dot in minus m dot out will be equal to change of this control mass in the control with the time, right? So this steady means that this term is 0. It's not changing, so it means that the flow inside this control volume is steady, means that it's not changing with time. Okay, so basically this means that this term will go to 0. And what is telling us? So it's telling us that from this equation, we will know that m dot in will be equal to m dot out. So how much of the flow into the system will be just equal to how much of flow flowing out. Okay, and so how the mass flow is calculated? You know, they're using small m is same thing actually. The mass flow rate is calculated based on the your velocity. This is v, the velocity is not volume. Okay, in this textbook, they're using this as the volume and this as the v. Okay, this is volume, and this is for the velocity. Okay, so you see that there is a bar in the middle that is volume, and without this bar, it will be the velocity. So mass flow rate is calculated that the density of the fluid times so mass flow rate is the density of the fluid times the velocity times the area. Okay, so this is how we calculate the mass flow rate, and you can compare the unit on the both sides. Okay, you will see that you will get the same unit, the kilogram per second, if you're using the SI unit for mass flow rate. So why? Because that you know, so let me give you an example why why we got this. Okay, so you see that rho times volume, you will get the mass, right? Rho times the volume, you will get the mass, and this volume will be just equal to the length of mass flow in, right? So how long this how long if you want to calculate a container, right? So it will be how long this x location this side will be times this cross-sectional area. Yeah. So it will be x times a will be your total volume. So rho will be times that. And then if you want to calculate mass flow rate, you want to divide it by this x times a divided by t will be this m times t, right? So this is the m dot, and this x times t is just the velocity, okay, flow velocity. So that's why is that is rho va give you the mass flow rate, okay. So this is just an explanation here. Let me remove this. All right, so that means that if you're using this equation, so that means that this rho, because rho is the fluid density, okay? Fluid density of the inlet velocity times this cross-sectional area at the inlet will be just equal to, density of times the velocity at the outlet. O means outlet, I means inlet, okay? Times this A of O. So that's why we get this equation here. Okay, using E, not O, okay? Exit, not outlet, okay? Exit. And since we know the diameter at the inlet and outlet, at the inlet diameter is 50 millimeter, at the outlet the diameter is 30 meter, and also we know the inlet velocity. So we know this term, and from this di, we can calculate this term. So this is the pi of di squared, right? Di squared divided by 4. Okay? So this will be the inlet of cross-sectional area, and also that we know this part, right? this is the outlet area, so cross-sectional area. So this will be pi times d O squared divided by 4. And we assume fluid density is not changed, so density is cancelled on the both sides. And by this way, you can just calculate this way directly by dividing this outlet cross-sectional area at both times. Okay, so that's the reason you get this equation here, and where you can calculate the outlet velocity. Okay, so this is an example that how you can using the mass conservation. Okay, so this is the most important part. Okay, so mass conservation that you can calculate the outlet velocity if you know the inlet velocity. Okay. So do you have any question for this example problem?
Professor?
Oh,
Yes.
Sorry, you go.
Oh, thank you. So just to clarify, the word steady just implies that the mass flow rate, or can you just repeat again what the term steady, I guess, implies? Just that the mass flow rate doesn't change?
Okay. So for control volume, okay. So steady state basically means that no change with time. So that means that all the term regarding this partial t, if t is time, all these terms will going to 0.
Mm.
For the unsteady state, that means that properties change with time. Okay, so it means that all these terms will not equal to 0. Okay.
Okay.
Professor?
Yes.
Why is it 2.7 meters per second at the bottom next to velocity out or exit when when the given was 2.5?
It's coming from this equation here. Okay. And this VI is the inlet velocity, right? This 2.5 here. Oh, okay. The book has a typo. Thank you for that. Just realized. So I got this from an old edition. So maybe your textbook won't have this issue. So this will be 2.5.
Okay, thank you.
So no problem. Yeah. So this value will also be different. Okay. So something else. Okay. You can correct it yourself. Okay. If there is no question, I will continue. And so now we introducing two methods, right? We can study the fluid in a system, or we can study a flow, go through a control volume. Okay, we have two ways, and these two ways will lead in two different description method for the fluid. So what this description method means? This means that if we want to describe how this how this flow is moving, right? This how this flow motion will be. So how the flow field will look like. We need to know that the velocity. We need to know the density. We need to know the pressure of all these properties for the flow. How we describe that? There are two ways to do that. Okay, the first way is called the Lagrangian way, which means that in the Lagrangian way, okay, so this is tied to system, which means that we try to describe the flow, based on the mass, not based on the volume, not based on their physical location. Okay, so if we, for example, if this flow, okay, if we have this fluid particle, a particle here, okay, and I want to observe this particle. I want to tag to this particle. Okay, I want to observe this particle. And if this particle is this is t0. Okay, if at t equal to 1, this particle is moving to another location. Okay, xa. So this will xa of t. So this is t equal to t. Okay, time, and then we will have a new velocity v of a equal to a function of t. So I will just saying that I will just describe the location, the velocity of this particle at the time. Okay, so which means that my observation is go together with this particle, is following this mass. Okay, similar for things. Okay, similar thing for this for the B location. It's like so if I have at B, okay, if at the time of t, this particle B is moving to this location and they have a new velocity v of B at this time. Okay, so by doing this, okay, if I can monitor all the particles in this fluid, okay, no matter it's million, billion, or infinite number of particles. If it is possible, okay, I can monitor all the particles in the fluid, and for each particle, I can give all this description, these equations for each particle. Okay, not one particle. For every particle, I can give that. If I know the time, I can know where is the location, where is the pressure will be, or where is the velocity will be. Okay, v of t. Okay, and so on. Okay. So this is called the Lagrangian wave distribution. So you already immediately can see the problem here, right? So if you're using the Lagrangian way to study, you have to track all the particles. In the fluid mechanics, it's almost impossible. But in the some other, like your dynamic class, right? Like if you want to track a rigid body, like go to the Newton's second law. Okay, you have a rigid body here. You give a force, and you want to track that how is the velocity, and or how their velocity will be. That is easy, okay, because you can think like the whole body is just one single point, and you can using this Lagrangian way that to see that okay, at the time of t, where the location will be, where the velocity will be. But in the fluid, you cannot do that, okay, because there are so many particles there. We cannot just track each particle, right? So this is the first method, which is tied to the system view. And the second method is called the Euler description of fluid. So this is tied to the control volume, okay? CV. So this
Professor?
is tied to control. Sorry?
Just before you do this explanation, can you just go back to the Lagrangian description for a second? I don't understand what it means when it says that the particles are marked.
So the particles are marked means that if I have experiments equipment, right, I only measure this particle. I won't, so all the, I only my observation, okay, I only focusing on this particle. So that means that all this equation I have here is only for this single particle. Okay, and if you want to know the position and the velocity of another particle, you have to give an additional, a new set of this equation for another particle. Okay. I'm talking. So all this equation is, for example, all this is for XA, okay, IA, CA. So this is for this particle. All this equation is only for this particle. And if I want to know the flow motion of the second particle, then I have to write a new equation for XB equal to XB of t. I want to search what it will be, and so on. Okay. Do you understand this?
Yeah, I got it. Thank you.
Yeah. So I will give more explanation in the future slides. Okay. And the second way, okay, is tied to control volume, which we call the Euler way. Okay. In this method, we do not focusing on single particle. Okay. We just focusing on the space location. Instead of measure each particle, we just measure this location. Okay. If I have a position x, y, z is fixed. Okay. If, for example, I want to measure this location, I just need to report that what it will be u of at this location regarding to time, what v of this location regarding to time, what w of this location regarding to time. Okay, I just put my my experimental equipment at this point. I don't change it. I don't care which fluid particle is going. It will be at the moment. I just want to know that at a time, if I given a time here, what's this UVWP at this specific location. Okay, so this is the Euler description of the fluid flow. Okay, which means so in this case, instead of tracking by mass, we just tracking the properties by location. Okay, physical location. And so one more comparison, okay, to make you feel more, to try to explain what's the difference between the Euler and the Lagrangian, Euler and Lagrangian different approaches. Okay, so let's think about that there is a smoke, okay, going up from a chimney. Okay, so this is a chimney, and you know this green lines, okay, is where the smoke is going. Okay, so let's first looking for the Euler approach. Okay, Euler approach, as I told you, like they try to measure this fluid flow field by by mass, right? So in these cases, okay, let's assume that we want to try to attach our thermometer to some point at this at 0 point here. Okay, location 0 point here. Okay, sorry, my mistake. Okay, this is my Euler approach is tracked by space, not by mass. Okay, so Euler approach is the second approach we write here. Okay, in the Euler approach method, we try to track the properties by a location. Okay, so in this case, we just put, if we want to measure the fluid flow properties at this point, 0 point, we just put our thermometer to this point. Okay, we want to record that the temperature at this point, changing with the temperature. So the function we get is this temperature at this fixed location x0, y0 regarding the different times. So this is the Euler way to do it. And if I want to track, if I want to measure the fluid property of another location, I just move this thermometer to another location. Okay, and then fix it there and compare with the time. I just put an additional thermometer here. I can know that was a new, maybe at this point, I call it 1 point, then you will get this t equal to t of x1, y1 of time, right? So if I can measure all the flow points, okay, so eventually you can see that the whole flow field will be given as this t of x, y, z of t. This x, y, z will give you that where you measure the fluid properties, and t is the time. So this is the Euler way. And in the Lagrangian way is different. Okay, Lagrangian way is that we need to find a particle here. For example, if we want to measure the flow particle of this part, okay, and then I put my thermometer on this here at t equal to 0, okay, and then at this point we will know the temperature at t equal to 0, but at t equal to some other value, okay, not 0. So this particle may be already moving to another location, like here, following this streamline. Then I have to let my thermometer go together with this particle. Okay, I also need to measure this part. Okay, and so we will have another t. So this is t0. Okay, so they will get a t of a will be ta of t1. Okay, a new location here. So that means that so the equation you get will be just the t of a will be ta of t for this particle. And if and as I told you before, if you want to measure other particles, then you will also need to provide in tb equal to tb of t and so on. Okay, as long how many, no matter how, it depends on how many particles you want to observe. Okay, so this is the basic difference between the Euler approach and the Lagrangian approach. And so this is the summary here to seeing the difference. So you can see that we can apply the conservation laws to both Euler and Lagrangian approach, right? And we will get different equations. Okay, why? Because that I told you that Euler method is based on the control volume, right? So you mostly get the equation from based on control volume, and the Lagrangian is based on the system. You mostly get the equation for the system. Not only that, and also you can see that you using Euler method, you will see that the equation you get is the properties you get is as a function of location and time. And if you're using Lagrangian approach, the equation you get basically just for a single point, for a single mass particle, and it's only a function of time. Okay.
So, Professor, so would you say, let's say we do the Lagrange approach for many different particles, and if we take the average of those, would you say we get the Euler value, kind of?
You cannot just do your statement is partially correct, because that you are saying that we have to, if you use the Lagrange method, you have to measure all the particles. That is correct. If you want to get the information of the whole flow field. But the second part is not, because that you cannot just simply do the average, because that at a given time, right? So this particle here is that, and this is particle A, okay? And maybe I can define this is particle B as a, and as a both time, A is at this position, B is at this position. You just cannot average these two positions, okay? It doesn't give you anything, okay? You cannot just do simple averaging. It's not a sampling measurement that you measure this same position many times and then you get the, you can average it. No, because they are represent the different particles at different material, different location. So let me give you some right here in the equation form. Okay. So let me write it. That's what I see. So in the, if I using the Euler method, okay, Euler method. So if I want to measure temperature, right? So all I get is this T of X, Y, Z of T. If I can get this equation using Euler method, okay, and I put a lot of thermometer for different location, okay. So this is for different thermometer, okay, for different location, okay. Then I can get the temperature of the whole flow field, okay. For the Lagrangian. For the Lagrangian method, what do we need though? It's like we have this T of A of T. I have X of A of T. We have Y A of T. And we have Z A of T. Okay. So we need to, for this is for only for one particle, for particle A, okay. And then I also need to measure particle B for the same thing, T, and particle C for the same thing. I add all these, many numbers of particles, I add them all together. Then you can get the whole, temperature field at different T, okay. You know what I'm talking? So this is the difference. So basically is that your thermometer, so this is one thermometer for particle. And this is another thermometer for the second particle, okay. So then this is thermometer for another particle. So your thermometer is going with each particle. And this thermometer, you also need many thermometer here for the Euler method, but you just place the thermometer to different place. Okay, and in this case, thermometer is moving with the particle. In this case, thermometer, you just put in that location. Okay, so there is a way you can convert between each other. Okay, but that is very mathematical, so I won't, go through that part in this class. But if you, because both methods will give you the whole, decryption, okay, the complete decryption, how the temperature field will be under the whole, on the overall domain, okay, flow domain. So if you get there is a way you can convert between them, okay. But by math, basically it's like you have to using some coordinate transformation way, to do this, okay, based on the velocity, this kind of thing.
Oh.
You can thinking that, and yeah, another way you can just thinking that in the Lagrange method, okay, you can just thinking that you just like your coordinate system is moving with the particle, okay. Each particle has their own coordinate system or something like that. And in the Euler method, basically means that you have a global coordinate system and fixed there, that are not changing at all, something like that.
Okay, thank you. I understand the concept of Lagrangian, but in practicality, how do you keep track of one single particle like that?
Yeah, that's why I'm telling you that in the fluid mechanics, basically, we don't use the Lagrange method because it's impossible that you track all the particles. But in some other cases, like the example I gave you before in your dynamics class, right? So if you have a solid part, a solid atom, okay, and I want to calculate the kinematics of its way, where is the location, where is the velocity, then you can just because you can synchronize the whole solid at one single point, right? you can using Lagrangian you can using Lagrangian method for this. Then for your dynamic in your dynamic class without any issue, no problem. Think about it, you are F equal to M of A, right? This is your Newton's second law. So this is basically for a single point, right? So basically telling that the force on this one will be equal to the acceleration on this one, right? So this Newton's second law is indeed, okay, is a Lagrangian law. It's not a control volume law, okay? It's focusing on, this law is focusing on this one single point, okay? Single particle, go with the mass. So this is go with the mass, okay? Newton's second law. So that's why I'm saying that, so in fluid mechanics, we do not using the Lagrangian way. We just using the Euler way, okay? We do the control volume method because we just cannot able to track all the particles. There's no way to do that.
Right. Makes sense. Thank you.
Okay.
Professor.
Yes.
So for basically, to my understanding, the Euler's method is basically, in this example of the chimney, would be measuring the temperature in like a given area, I guess, and then
giving a location, giving
and then for Lagrange, it's just the temperature at a particular particle.
Yeah, you're absolutely correct. Okay, no problem. That is great. And so this is some summation, okay, and the last one is the last thing is important is that in the Euler, in the Lagrangian method, right? I told you that we try to track each fluid particles, right? But in another way, right? As I told you that there's so many particles in the fluid, right? We just cannot go to the molecular level, right? We just cannot track each molecule of the fluid particle, right? Is important. So you can thinking that the Lagrangian is try to get the particles, and Euler method we just do not think about particle anymore. We just thinking that the whole fluid is just a continuum medium. There's no there's no distance between molecules or something. We just neglect all of this particle behavior of the fluid. We just thinking that everything is continuous, okay, in the fluid. So this continuum concept is important, okay. That means that if we're using Lagrangian approach, we're using continuum method. In another way, okay, this is also telling us that in which cases we can using Lagrangian and in which cases we can using Euler. Usually, okay, if you in your future study, okay, if you want to do particle method, like if you do like a gas dynamics, okay, not the fluid, gas dynamics, like you want to track, each particle moving if the gas is very rare, or you want to track that some particle how they diffuse in a fluid, okay. If you want to using this so-called particle method, you should using the Lagrangian approach, okay. But if you try to study the fluid is not a particle, you try to thinking that the fluid is a continuum medium. It's not it's not like a particle by particle, but thinking that they are continuum. Then you're using the Euler approach. Okay. All right. So now we finished the topic of the Lagrangian and Euler method. And we will using the, as I told you, right, Lagrangian method is Euler method is what we use in fluid mechanics. So in the chapter 3 and chapter 4 future, when we try to derive those governing equations for the fluid statics and fluid dynamics. So you will I will show you that we will using this Lagrangian, we will using this ordering approach more, okay. So so during this lecture we will try to repeat this concept many times actually. Okay, the next topic is regarding the system of dimensions. Okay, so what dimensions means? Dimensions means like you can just thinking that it's a very fundamental physical characteristic, right? Like the length is a very fundamental properties. Time is one dimension of the physics, right? And also that you will have, we usually also think mass and temperature in fluid mechanics. Fluid, thinking mass and temperature as the fundamental dimensions of the fluid mechanics. So we call this length, time, mass, and temperature as the fundamental dimensions. is because that any other properties, okay, like the pressure, like the density, like the force, like the energy, all these kind of things can be represented by these 4 fundamental units. Okay, for example, okay, let's think about the force. We have the force, right? We know that it's from the Newton's second law, it will be equal to m times a. Okay, m is mass, right? So this is the mass. This is already the fundamental units, right? And a, we know that a is equal to dv dt, right? So we know that is and then the change of the velocity is d of length of dt, right? And then dt, right? Because velocity change is change of the length. So we know that for the a, we can write that this is basically L squared. Sorry, not L squared. L divided by d squared. So this will become L divided by t squared. So which means that if you have a force, okay, so basically the force itself is not will be a fundamental dimension because it can be represented by other dimension quantities. It can be represented by this mass dimension times length dimension divided by the square of time dimension. Okay, so by this way, so all the measurable quantities, okay, we can subdivide it into 2 groups. The first group is called the primary quantity, okay, and which is all these 4. So the 4 quantities we mentioned here: L for the length, small t for the time, m for the mass, and big T for the temperature. And we're also seeing that the secondary quantities, which means all the other properties which can be, can be expressible in terms of this primary quantities. Okay, force, pressure, density, energy, and all the other quantities can be, velocity, acceleration, vorticity, everything, okay, else can be thinking about as a secondary quantity. Okay, and so how to choose which will be the which quantity will be the primary quantity, right? So in the example I gave you before is we are using this way. We choose mass, length, and time and temperature as the primary quantity. And we also showing that using the Newton's second law, right? Basically, the force is related to mass and this length and also time. So if I do not using the mass and I choose the force as the primary quantity, then your mass cannot be the primary quantity. Okay. So between the force and the mass, because this is a correlation, you can only choose one of them as a primary quantity. Because that after you choose the mass, you can get force from the mass. And if you know the force, you can get the mass from the force, right? So the second way is that we replace the mass to force. Okay. So this is the second way, like a way, thinking like to represent the primary quantity for the dimensions. And there's special one. Okay? This is the last one, and this one is only the, North America is used in North America. Okay? And in this way, okay, you can see that both force and mass is used as the primary quantity. You may immediately feel that this is confusing, right? Because I already saying that, because of Newton's second law, this mass and this force, you can only choose one of them as the primary quantity because that from the Newton's second law, we know that the mass can be expressible from the force and the force can be expressible from the mass, right? If all the other 3 is true, actually. And why? The reason is very simple. It's not simple, okay? The reason is in this system, so-called FMLTT system, both force and mass is true as primary. Because the reason for that is because that in this system, this force is chosen as the LBM, LBF, the pound force. And in these cases, M is chosen as the LBM. Okay, and you can immediately see that the force and the mass, they are all defined by the pound, right? And there will be a conversion between them, right? Additional conversion between. What that conversion means? So if we're using this system, what the mass will be? What force will be Newton, right? And mass will be kilogram, right? And we know that we know that this is always working. F equal to m times L squared of t. For this one, it's working. And similar things for this system, for the second system, if I choose the F equal to Newton, mass equal to kilogram, we also, this one is satisfied. But in the third system, if you put this LBF, okay, pound force to the force, you put the pound mass to the mass, 1 pound force, 1 pound mass, and L you're using the feet, and time using second. This won't be satisfied, okay? And what does it mean? This means that in these cases, we do this correlation will not, this Newton's second law will not, in this, I'm not saying the Newton's second law is not applicable. I'm just saying that the Newton's second law in this equation form will not be correct. And we have to convert this equation into another form, which is F equal to m times A divided by G of C. Okay, and this G of C is a dimensional constant. It has a unit for it. Okay, and so you have to using a new form of this. Okay, so what does it mean? This means that in these cases we add both force and mass. Okay, but we choose the force, the unit from the force and mass that in a way that the traditional correlation, this FMA will not be available, and we have to set up a new correlations of and by introducing a new this conversion factor here. Okay, so this makes this case is very special. So basically we arbitrarily create some disagreement between F and M. Okay, so to make it looks like there is no correlation between them. So this is a very artificial way. Okay. And if you have confusion with this GFC, don't worry, I will give you more explanation about this. Okay.
Just a question.
Sure.
Isn't it so? If you're doing like the dimensional analysis for it, would it be just pound force is equal to pound mass over 32.2? Is that what you're?
Yes. This GC is 32.2. I will go there. Okay. Yeah. Just saying that this is a very special system. Okay. If you're using this system, a lot of equations that their equations will be modified with this GC. Okay. When you involve the force, the relation is between force and mass. Okay.
Okay. Thanks.
No problem.
Professor, will we be using the system of units in this class, or will we just be sticking to the conventional like SI, MLTT units?
I will go there, but I can tell you earlier is that we will focus on this unit here. Okay, and this tool is only for introduction, but in the whole book, okay, we focus on this MLTT method. But for this MLTT, we'll be using both SI unit and British unit. Okay. So we will go there. And so let me, yes.
I just had a quick question. When you define for acceleration for Newton's second law, would it be length over time squared? So it's meter per second squared?
You are absolutely correct. So this is really t squared. You are absolutely correct. Sorry for that. Yeah, so this is r t squared. Yeah, I think I read this in earlier state. Here is correct. Yeah.
Okay.
Yeah, so I will correct this typos in the PowerPoint I uploaded later on. Okay. And so this is the dimensions. Okay. Don't confusing with this dimension system with the unit system. Okay. Unit system belong to dimension, but it is not exactly the same as the dimension. Okay. And so for example, okay, you can use an SI unit for MLTT. Okay. And we can also have other unit system called the CGNS unit system, which means that for the mass I'm using the gram, for the length I'm using centimeter, I using S and K. Okay, these are another unit system for the MLTT. So for different dimensions, for dimensions we can have many unit systems. Okay, and for the SI unit, Yeah, it's for the MLTT. And for this British gravitational unit, I also, you can also call it just BG unit, okay? It's for the FLTT because it's using pound force. And this E unit, so that you will have for the FMLTT, you'll have both force, both mass, length, time, and temperature. Okay.
Is degree or is that Reynolds? Is that what that
This
is?
is the ranking degree for the temperature.
Okay, thanks.
Yeah, ranking for the temperature. So this is the Kelvin for the temperature. So you can see that what for the force, okay. So for different, so this is a comparison here, okay. For what's the default unit for different unit system. So for the SI unit, force is Newton, and mass is the kilogram, and length is meter, temperature is Kelvin. And for the BG system, force is the pound force, mass is the slug, okay, and slug is one slug will be equal to F equal to ma, right? So one slug will be equal to this mass here will be the where is mass? So, what am I writing? So many things. So m will be equal to F divided by A, right? So one slug in this case will be equal to the force will be LBF divided by this length, feet square divided by second. Okay, so by this way, the slug, what slug will be, and if you're using this rule, and temperature for both BG and EE is using the ranking. Okay? And EE method is very special because that additional GC parameters. And let me give you an example for each unit system. Okay, so for the SI unit, right, mass is the kilogram, length is the mass, length is the meter, time is second, and temperature is Kelvin. And if you're using the Newton's second law, you can derive that F equal to ma, right? F is 1 Newton will be equal to 1 kilogram times the meter per second square. So this is, you know, that you can get the conversion between the Newton and this kilogram meter and a second, I think. And in the BG unit, in the same thing, okay? Because force is known, okay? So we can calculate the mass from it. So one slug will be 1 pound force divided by this this A here will be feet per second, so per square second, per second square. Some you guys are chatting? Okay. All right. So and then for the EE unit, because we're using both force and mass, right? And I told you that so there will be an additional conversion factor, which is called GC, will be introduced. So in this case, okay, your Newton's second law will be F equal to ma divided by GC here, and 1 pound force will be equal to 1 pound mass, and times this A here, okay, this is the gravity acceleration, okay, and divided by this GC. So this is because why this is the gravity acceleration, because in this system 1 pound force is defined as the the weight of 1 pound mass under the gravity. Okay, so this is the definition between this. So that's why this A has to be the gravity of the the Earth's gravity acceleration, and then divided by GC. So by this way, you know that this GC constant is this one, and with this additional unit here. So it's not a dimension. It is not a dimensionless parameter. Okay, it has the units for this GC. And so particular things that in the EE unit, all the equations will be looks different when you involve the force and mass. Okay, you will obviously when you involve force and mass, you have to add this multiplication for because it's GC. Okay, and we have this three major system, SI, BG, and EE, right? So in this book, we only focusing on the first two, the SI unit and the British unit. Okay. So there is a example problem, okay, on how to convert the unit between the different unit system, right? How I convert the length from the SI to BG or to E. and those other things. So I will leave this, this example problem to next week's recitation. Okay. So we don't do that. And one last thing regarding to the units is that if you have an equation, okay, you need to make sure that the dimensions on this equation is consistent. What does this mean? This simply means that if you try to calculate calculate the dimensions of each term, okay, in this equation, they should all have the same if they all should have the same dimension. If it's expressed in those fundamental, quantities. Let me give you an example. Okay, this is one equation here. Okay, this equation is called the Bernoulli equation, which you will learn this in the fluid statics in the chapter 2. Okay. So you can see that this equation will contain 6 terms, right? And this is the pressure divided by density. This is the velocity squared divided by 2, and this is the gravity times the elevation, z. Okay. And on the right hand side is the similar things. Okay. So the consistency I'm talking about, it just means that if you try to get the dimension of the first term, okay, because for the pressure, right, pressure P equal to F divided by the surface area, right, and F equal to M of A divided by surface area, right? Area. Yeah. And if you want to calculate dimension of it, so for the pressure, so it will dimensions will be mass times this LT squared divided by L squared, right? M is the dimension for the mass. This L divided by T squared is the dimension for the acceleration. For area is just L squared, the length squared, right? And then we will know that for the pressure, their dimension will be M times M divided by L divided by T squared. Basically, is this one. Okay. And similar thing for the density. Density is M divided by volume, right? So density will be just the mass divided by length to the cube, because length to the cube is the volume. And if you combine these two, you will see that okay, this term P over rho, their dimension will be just this term divided by this term. You will get this result will be equal to L squared divided by T squared. Okay, so this will be dimension for the first term. And similarly, you can do the dimension for the second term, for the velocity. Okay. So for the velocity, you will have, we know that velocity is the length divided by time, right? And then its square will be velocity square divided by 2. You will also have the same dimension, length square divided by t square. So you will see that for this term and the second term, they will have the same dimension, right? Because they are all can all in the dimension of L squared divided by T squared. And similarly, you can do the third term, which is acceleration times the length, right? So acceleration is L divided by T squared, and this length is just L. So you time them together, it's also L squared divided by T squared. So by this way, you can see that this equation is consistent in dimension, because all the linear terms, each term, they have the same dimension. Okay, so what does this mean? That means that when you have this equal sign here, okay, on the left hand side, right hand side, not only the quantity, the value, you need to be consistent. The value on the left hand side and on the value on the right hand side. So dimension, all you can see in the units, okay, also need to be consistent. The dimension on the left hand side and the dimension on the right hand side should be the same. Okay, if you write them this dimension in units term, they all can be convertible from left to right, right to left. Okay, so this is so-called consistency in dimension. So do you have any question here? No? Okay, good. All right, so the last topic, okay. The last topic for this chapter is for the experiments, okay. Is introducing the experimental error, okay. And so you know that in the fluid mechanics, when we try to using this, this experimental, equipment to measure the quantities, right? We get the value, okay? We get experimental values we measure, but because that some errors during the experiments, these conditions, okay, you cannot 100% accurate, okay? You always bring some error due to during the process of this measurement, experimental measurements, and this error, okay, is called the uncertainties, okay. So basically, from the measurement, you will get the best estimate, okay, the value I report from my measurement. Okay, in this case, I measure this mass is 400 gram. Okay, so if I have a scale, okay, if I have scale, okay, I have this mass here. Okay, I measure it like this is 400 gram. Okay, I know that this is what I measured, but I also know that this scale, okay, they may come during this measurement, maybe there are some additional error. For example, like some friction, friction effect during the spring of this scale, okay. Because this scale is too old, not brand new or something, and I thought some lubrication issue or something, or even like when I'm doing the measurement, maybe some wind is there is some direction of the wind which is causing some momentum force, blowing into this scale, giving me some additional weight or something. So we will also know that there will be some uncertainty, okay, for this measurement quantities, and the in the engineering, the way we write this is using this format, to report the experimental data. We write our best estimation, and we also add this plus minus sign, and also seeing that what's the confidence of this our experimental result. So in these cases, we estimate the uncertainty is 2 gram, which means that I'm confident for my experimental data between 398 to 402. Okay, I'm confident the result will be in this range. Okay, and this uncertainty term here can also be expressed in a percentage way, which is called the U. Okay, this U means the uncertainty. Okay, so that's why it's U. And so uncertainty of this mass M, this mass here, will be just equal to this additional value plus minus 2 gram divided by your best estimate 400 G. And so it will be plus minus 0.005, or you can see that it is plus minus 0.5%. So you can also, seeing that, okay, my measurement result is 400 G, and the uncertainty is plus minus 0.5%. Okay, so this is how we do the, how you report experimental data with this, with the uncertainty. And let me give you an example here, how we do that. So we want to use this ruler, right, to measure the diameter of this tennis ball, okay. And let's first look at this ruler. Okay, this ruler is I think the fundamental unit is a centimeter, and the smallest ticks is 0.1 centimeter. Okay, so this is 1 centimeter, and you have 10 ticks here. Okay, but you will see that first, okay, you want to measure it, you have to a line here, a line here, right? First, you will see that during this experiment, okay, it's very hard to land the edge of this ball to this ruler, right? Because when you draw this line, it's very hard to do that. Okay. Although that and also that although we know that the smallest tick, okay, is 0.1 centimeter, you have 10 ticks here, but because this picture is blur, and maybe I can because my eyesight, okay, I can only see that this length here. We can only see like this 0.5 centimeter very clearly. I cannot see these very small ticks for each 0.1 centimeter. I only can able to see 0.5 anyway clearly. Okay, and then in these cases, okay, I can just think that okay, I'm confident that for my measurement result by this 0.5 divided by 2. Okay, because that why divided by 2? Because that although I can clearly see this 0.5 ticks, but I'm not sure that the one is, because we have this plus minus things, right? I'm not sure that the way I measured is too much or too small, so I just divided by this by 2. This is so I can estimate that my error range is around 0.25. And usually in this uncertainty, report, we just report 1 digit, okay? So we can see that approximately is 0.2, okay? So in these cases, I will see that, okay, from my measurement, I'm confident that, the error will be about 0.2 centimeter, okay? So in these cases, when I report the result, okay, so on the left-hand side, I read is 50.2, and on the right, I read 56.5. So you're using this one minus this one, okay, I see the diameter is 6.3 centimeter. But then I will also add that my confidence limit. So I'm only confident with the result, with plus minus 0.2 centimeter. So this is how we do experiments and report uncertainties. Okay, and this is some actual topics. Okay, you do not need this for this class, but I will just spend 1 or 2 minutes for this. Okay, so if I have, this is showing that how the propagation of the uncertainty. For that, this means that if I want to measurement a quantity of R, okay, and this R contains many independent variables, this x1, x2, xn, right? And when in the experiments, I need to experiment measure the data for each x value, okay? And because this is experimental data, right? So for each experimental measurement for this x, I will have their own uncertainty for this xi, right? And after I bring all the uncertainties for each x value, so what will be the overall uncertainty for this R will be? Okay, so it can be simply calculated based on this differential equations. Okay, we know that the change of big R will be the change of big R partial gradient on this xi times this is the small change of delta xi. Okay, so by using these correlations, we can calculate that the overall and change of this R on the ideal on this xi independent variable will be just equal to this delta I or delta Ri divided by this R. Okay, so you bring this to here, so you 1 over R to this one. And then you times xi on here and divided by additional xi here. So this will be cancelled, so this will be same here. And you know that this quantity here is basically just uncertainty of xi. Okay, so by this equation, we can know that uncertainty, the contribution of uncertainty of this xi in variable to this overall R is calculated by this one. Okay, and then if you want to calculate the overall uncertainty, will be just plus minus, and then you do add the square of this one, add them together and divide by 1 to get the overall R. So this is some additional topic. Okay, it's in the appendix of your textbook. Okay, so if you're interested in this one, you can try to read this in your appendix. Okay, it's appendix E on your textbook. Okay, and so I also give an example problem like how to really use these correlations. Okay, and E or F. Okay, depending on your addition. Okay, your textbook. So if you're interested, you can go through this example problem yourself. Okay, and so do you guys have any questions? No? Okay. So just want to let you know that this experimental error part is is not required for the exam. Okay, so just some additional topics for you guys. And here we finish the content in the chapter 1. Okay, it's just some fundamental introduction for the fluid mechanics and the method we use to study the fluid mechanics. And the next lecture we are going to go to the chapter 2. We'll try to introduce some fundamental concepts we use in the fluid mechanics, like those velocity, like the viscosity, like those streamline, streakline, and so on. Okay. And if there are no question, I will just finish my lecture here, and I will see you on next Monday. And for the chapter 1, we do not have any homework, okay? And on the blackboard, I set up the VD class, and also set up a test, assignment for this chapter 1. So just for the practice. So if you are interested, want to know how to using the VD class for homework, you can just try that, assignment, and that assignment won't be graded, okay? Any question here?
Professor.
Yes.
Where can we find Appendix A?
What do you mean?
One of the questions for the homework you assigned, it said to look at Appendix A, and I was wondering where we could find that.
Appendix A. Do you have your textbook? It should be on your textbook, right? At the end of the textbook, because that is the version of textbook I have is the instructor version. It's not totally same with the same version as you. So Appendix A is the fluid property data. So you can find all the density and specific heat and this kind of thing in the Appendix A. You should be able to find it in your textbook, actually.
Do you think you could post copies of it under documents in Blackboard or something?
Okay, I will try. Okay.
Thank you.
I mean, let me find it because let me find some electronic version of the book so that I can copy it and post it there. Okay. Any other question? Yes.
I just have a question about like if I get the hard copy. I purchased the 7th edition. So I just wanted to use the text for its actual material rather than the problems, because I know on the problems we're going to be using Wiley. So the 7th edition should be fine, right?
So the 7th edition should be fine for your reading. Okay, if you want to reading this the content of the book, it should be fine. And Wiley Plus is doesn't matter which edition you use, because that when you purchase the correct code, you will have the same problem actually, no matter what you have. So for 7th edition, you should be fine. You should be fine. But you just also go through this lecture notes, because maybe some notation will be different or something. I'm not sure because I didn't use it. I do not use the 7th edition.
Yeah. Okay, that's fine. I'll use them in tandem. Thank you, Professor. Have a great weekend.
Okay. Any more questions, guys?
Professor, I just had a quick question about the textbook.
Sure.
So can we get the textbook that you mentioned in the syllabus? Is that okay? Because I remember you were saying you were talking with the publishers if the Wiley code was okay.
Yeah. I send so textbook, textbook and Wiley Plus code is two different things. Okay. For textbook, I basically what I'm seeing on the blackboard is that I believe both 9th edition and 10th edition should be fine. And the latest edition is 10th edition is the edition I have. And the bookstore in Stony Brook University, they are selling the 9th edition, not the 10th edition. If you want to get that one, it's also fine. And some other students saying that okay, I also want, maybe I have some older edition. To me, I think it also should be okay, because if you just use it for reading, but just be careful that to make sure that maybe some notation is changed, maybe some notation letter is different. So you need to be aware that if you go through with my lecture notes, okay. And for the Wiley Plus code, you have 2 ways to purchase it. You can purchase it from the bookstore with the 9th edition coming with it. That one should work. And I also, on the blackboard, I posted what the product code for the Wiley Plus. So when you do the purchase, and you can ask the people there to make sure that access code is for that product code.
Okay.
And but if you want to play safety, you can just purchase the access code from the link inside the blackboard, because when you click the Wiley Plus, if you do not have the access code, they will redirect you to some web pages so you can purchase the code directly. Okay.
Okay. Is there some class code that we need for the Wiley Plus from you, like you know what I mean, to get the homework for this class specifically, or? Yeah, no, this Wiley Plus, we just use this for the homework problems. So basically, I will assign the homeworks problem on the Wiley Plus. But Wiley Plus definitely has more functionality. It's basically an interactive book environment. So you can also use it for for some reading and exercise there. No problem. I think more resources there. I understand that, but I was just wondering, meaning is there a code that we have to input to get, meaning the homework that you're assigning? You know what I mean? That it's specifically for the class that you're teaching. You know what I mean? Almost like with Connect or Pearson, how we have to get a code.
Yeah, that's why I mentioned that product code, right, on the Blackboard announcement. That product code is for this class.
Okay.
Yeah, so when just ask people there that make sure that if you buy it from Bootstrap, make sure that ask them that if this access code working for this product. If they cannot confirm it, do not buy it from the Bootstrap. You can just directly buy it from the web one. I believe the web one maybe a little bit cheaper. Okay, you should try to compare the price before you make a decision where to buy.
Okay. Thank you, Professor. Have a good day.
Any more questions, guys? Okay, so I'll see you guys on Monday. Bye, everyone.